This is part 1 of Unit 6, Lesson 2, Summation Notation, Writing Area as a Limit. So this topic is going to cover not only how to set up a Riemann sum, but how to go back and forth between the definite integral notation and the summation notation. So our sigma notation gives us a compact way to write a Riemann sum as a single expression. So we're going to lay the foundation for what exactly a definite integral is, which we're going to take up in the next lesson in more detail. So we did do some summation notations in pre-calculus. We are going to be writing them in this one based on some given information. So just to review, or if you've never seen this before, our summation notation is a way to sum up a finite number of terms. So we use the Greek letter sigma for the operator that tells you that you're going to be adding up all these terms. So we have the index is summation, which tells us where we start. And we use the letter K and M are used a lot. But we're going to use our lower notation as K, and it tells us what term we're starting counting with. It might be the 0th term, it might be the 1st term, it could be the 5th term. Mostly we're going to be focusing on using K as 0 or 1. And then we have our expression, which is in terms of our index K, and then the upper number is the stopping limit. Like how many terms are we going to count? Are we going to count 4, 5, 20, or maybe we're going to count an infinite number, which is what we're going to get to as we go through this lesson. So to evaluate this, here's our expression, 3k minus 2, and we're going to start at the first counter as 1, and we want to count 4 terms. So to set this up, we first want to recognize that we're going to be substituting in k equals 1, 2, 3, and 4. So when we do this, we're going to have 4 substitutions here. So the first term will be 3 times 1 minus 2. And then to that, we're going to add 3 times 2 minus 2. And then we're going to add the third term, which will be 3 times 3 minus 2. And then finally, the last term we're adding is 3 times 4 minus 2. And then you just determine what all those are. So the first one is 1 plus 4 plus 7 plus 10. And when you add those all together, this summation equals 22. So that's the basics of using the summation notation. Okay, so now for this one, consider the sum 9, 25, 49 plus 81. So 2 of these answers are correct. So I'm going to pause for a second and see if you can determine which 2 would give you those 2. I'm sorry, which 2 of the 4 choices would give you that sum? If you chose letter C and letter B, you would be correct. Both of those will give you that set of numbers. If you notice, the biggest difference is the starting index. And in this case, we start at 1, so we need to count to 4. And this expression gives us odd numbers. And the other one, we're starting at 0, so we're going to count the 0th term, so we only need to count the 3. And this expression also gives us odd numbers. Okay. So it is acceptable to use any letter for the index, as I said. Most textbooks use I, K, or N. Be aware that some summation expressions may have other variables. As we will see, we're still going to have some x's in them sometimes. Okay? So this will help you understand summation notation represented a Riemann sum. So if you have f of x sub I star, so you're going to be adding the function, substituting each different value of x in there. Okay, example 3. For the function y equals the square root of x, we're going to draw rectangles forming a right-hand sum with 6 equal subdivisions, n equals 6, on the interval from 1 to 4, where the width of each rectangle is, as we've used in the past, delta x equals b minus a over n. So let's start by drawing a picture. So we're going from the right, so let me just start at the end here. So our last rectangle will end at 4, and so it's going to be with n equals 6. Let me not jump ahead. So a is 1, b is 4, so our delta x is going to be 4 minus 1 over 6, which will be 3 over 6, which is 1/2. So each rectangle is going to be 1/2 wide. So there's 1, there's 2, there's 3, there's 4, there's 5, and there's my 6th one. So I have 6 rectangles. 1, 2, 3, 4, 5, 6. Okay. So now what we're going to do is we're going to find a general expression for the area of the kth rectangle, so a sub k. So you take the area of the first plus the area of the second plus the area of the third plus the area of the fourth plus the area of the fifth plus the area of 6. So here's what the summation notation looks like in general. So we're going to break this down into steps and add the details so we can directly figure out the value. Okay, so the height of each rectangle is a function of the right-hand endpoint of the rectangle. So it's going to be a plus delta x times k. Okay, we need the a here just in case we're not starting at 0 like we are in this one. We're starting at 1. So our a sub k is going to be 1 plus our delta x, which is 1/2, times k. And we usually write the k on top of the fraction like this. Okay? Now, to get the width or area of the rectangle, we have to take width times height. So we have our k, where each rectangle gets substituted here into the function. We know how wide they are. Their width is 1/2. So now we can write an expression for their area. So their area at any k is going to be delta x times f of k sub x. So in our case, it's going to be our delta x, which is 1/2, and our function is the square root of x. So it's going to be the square root of 1 plus k over 2. And if you want, you can write that as decimals, which I think I'm going to do because I think it'll be a little easier to show the expression going forward. So I won't have as many fractions and everything. Like that. Okay. So that's our area. And now we're going to write the summation notation for the values of k from 1 to 4. So we're going to write our sigma. We're going to start at 1 to 6 because we have 6 rectangles. And so this is going to look like this. The 1 to 4 is built into the expression here that I'm writing right now that we found in parts A through C. Okay, but we wanted 6 rectangles. So this is approximately equal to 49.11. All right, so here's the basic overview of what we're doing. We're going to make sure that we first find the width of each rectangle using our delta x equals b minus a over n. And then after that, we want to find the right endpoint of each end. We're going to assume we're doing right-hand sums. The right endpoint, x sub k, is equal to a plus delta x times k. And then we find the area of each rectangle by taking our delta x times substituting that x sub k into our function. And then we go from 1 to how many rectangles we're creating. And if we're doing a left-hand sum, we go from 0 to n minus 1. and that will still give us the same answer. Okay, so use the procedure above to write each expression that represents an approximation shown. So what you're to do is to look at these four expressions and determine which one is the correct one for the approximation we see here. So a couple of things. First thing is to recognize that A and B have to go because they don't have the delta x. As you can see, our delta x here is 1/2. So these two are the only ones that have a delta x, so they're out. So the next thing you have to figure out is, do you have a right-hand sum or a left-hand sum? And if you notice, our rectangles are touching on the right-hand side, so it can't be D, so it has to be C. Okay? There is our expression for that graph. Okay, next. A definite integral represents the area under a curve of a function. A Riemann sum gives us an approximation of that area. Imagine if we can create an infinite number of partitions, as we've talked about in class. So what we're going to do then is we're going to take the limit as our Riemann sum as n, and we're just going to make n infinitely large. So we're just going to keep making smaller and smaller subdivisions. And by doing that, what we end up doing is creating our definite integral there. So our definite integral, our area under the curve, is defined as the limit as n approaches infinity of our sum of rectangles. Okay, so here is the definition of a definite integral. We've been dancing around this in the last lesson and this one. So the definite integral of a continuous function, f of x, over the interval, the closed interval a to b, is denoted by the integral from a to b of f of x dx. It is the limit of the Riemann sum as the number of subdivisions approaches infinity. So there it is, laid out there for you, and you want to remember that x sub k equals a plus delta x times k, and delta x equals b minus a over n. So let's do another example here. So given the graph of the function on the interval 0 to 4, this exact area can be represented using this definite integral notation. So that this part of the definite integral is representing that curve there. So the area under a curve is represented by adding the integral notation. So what we are to do is to write the Riemann sum for this integral. So here's how we want to go about doing this. We want to first start by finding our a and b. So as we can see that from the graph or from the definite integral, we can see that a is 0 and b is 4. And can we see that here? Because our shaded area starts here at 0 and ends at 4. So now we can find our delta x, which is b minus a over n. And we can make as many rectangles as we want, but what seems to make sense here, because remember, the more rectangles you have, the better, is if we divide this area up into halves here. So we're going to let that equal 1/2. Okay? So we're going to have that, if we do that, we have 1, 2, 3, 4, 5, 6, 7, 8 intervals. So our delta x ends up being 1/2 if we do 4 minus 0 over 8. So we get 1/2. So however you want to do it. From the graph, create 8 rectangles and then figure out how wide they are, or you can pick a width. Okay, so now the other thing we need is we did our delta x, our x sub k. So we get that by taking a plus our delta x times k. So in this case, our a is 0, our delta x is 1/2, and we have k. So x sub k is just going to be 0.5 k. So now we can write our Riemann sum. So our integral from 0 to 4 of 1/2 x squared plus 1 dx is the same as taking the limit as n approaches infinity of the sum of k equals 1 to 8. I'm sorry, n, because we're going to take it to infinity. 1 to n of, taking our function, 1/2, and we substitute in now our x sub k, so that's 0.5k squared plus 1. And we multiply that times our delta x. And there's our Riemann sum. Okay, so we're to use our calculator to evaluate this definite integral and then find the corresponding Riemann sum for this definite integral. So just using our calculator here, let's go ahead and go under math and choose number 9. And we're going to put in there 1 to 2, and our expression is x plus 1, and our variable is x. And we hit enter, and we get 2.5. Okay, so when we evaluate this, we get 2.5. Find the corresponding Riemann sum. So the width of this is going to be, we have to figure that out over here. So we have an A of 1. And a B of 2. So delta x is b minus a over n. So that's going to be 2 minus 1 over n. So that's 1 over n. So we have a width of 1 over n. And now our x sub k is a plus delta x k. So in this case, it's going to be 1 plus k over n. So 1 plus k over n. The height of each rectangle then is going to be, substituting it in our expression, x plus 1. That is going to equal, so now we have 1 plus k over n, and then we have our plus 1. So let me write that in another color so you can see the final answer. We get, so we have 1 plus 1, so we get 2 plus k over n. So now we can write our Riemann sum. So our Riemann sum is going to be the limit as n approaches infinity of k equals 1 to n of 2 plus k over n. That's our x plus 1, and then times our delta x, which is 1 over n. So if we simplify that a little bit, we can write it this way. The limit as n approaches infinity of our summation of k equals 1 to n is going to be 2 over n. Actually, one thing you can do here, let's make this a little easier. I can pull out the 1 over n, and I can just have 2, whoops, I forgot my summation, because that's already at n, and it's going to be just a common term that was distributed. So this is just going to be 2 plus k over n. There we go. All right, evaluate the Riemann sum on your calculator. What is the answer? I'll leave that for you to find that it is also 2.5, and we will stop there.